like that, a counter may count say 4 pulse. That means it should have 4 distinct states. If you want to count 6 pulses, so your counter should have 6 distinct states. Normally, a counter counts say like 0, maybe a state as 0, then 1, then 2, then 3, dot say n, or n minus 1, n minus 2, dot 3, 2, 1, 0, like this. So it can count, or its states may be towards up direction or downwards directions, okay, depending on the states. And depending on the sequence, there are 2 types of counter. One is up counter. If your counter go on counting or changing its states like 0, 1, 2, 3, 4, like this, then it is up counter. If your counter changes its states like say 4, 3, 2, 1, 0, like this, then your down counters, okay. And normally, if you use say n number of flip-flops in your counter, then normally, ideally, your counter can count 2 to the power n states, because then your circuit will have 2 to the power n states. For example, if you want to count say 4 states, then you need 2 to the power 2. That means you need 2 flip-flops. Okay. At the same time, if you want to count 8 pulses, that means if you need to have your counter should have unique 8 independent states, then you need 2 to the power 3, that means 3 flip-flops. But there may be case like that, you want to count 6 states. So in that case, you have to use 3. So all states of the counter may not be used. Okay, so you have to do some kind of modification so that while counting 1, 2, 3, 4, 5, 6, then it should go initial state, that is 0. We will see this. Okay, so all the states of a counter may not be utilized. Okay, depending on the requirement or design of your circuit. So there are 2 types of counter: up counter, down counter. Number of flip-flops required in a counter is 2 to the power n is the total states of the counter, and n is the number of flip-flops. Okay, so even if you use n number of flip-flop, counts or states may be less than 2 to the power n also, if you don't use all the states. Okay, again, based on the operation, that is change of the outputs, there are again 2 types of counter. One is asynchronous, another is synchronous counter. Okay, so in asynchronous counter, your states are changed automatically. In synchronous counter, your states will change based on some other signal, that is synchronous with other signal. Okay, so asynchronous or ripple counter, also known as ripple counter, these are faster because automatically output will change as soon as you switch on your circuit. Okay, but in synchronous, your circuit will change only when you change some other signals. That is, its change is, or operation is synchronous with some other signal or some other circuitry. Okay, so let us take say an example. So this is a 2-bit up counter. Okay, can you see it? Sagarika?
Yes, sir.
Okay, so this is a 2-bit, 2-bit up counter. Okay, so maximum number of states it can count 2 to the power 2, that means 4. Okay, so these are basically T flip-flop. We have modified JK flip-flop, just connecting both the J and K inputs. You see here also. Okay, so this is a T flip-flop. This is again a T flip-flop, and in T flip-flop, as long as T is equal to 1, output will toggle between 1 and 0. Okay, and you see the output of this T flip-flop is used as a clock of here. Okay, so another issue here, you see here. Huh? Okay, here you see we have already know that key during output will change based on the clock, and again modification was there key during on the edges of the clock, that is either positive triggered or negative triggered. So this is the symbol. If symbol is like this, that means positive triggered. If like this, then this is negative triggered. So this is a negative triggered. Okay, this is a negative triggered. Okay, clock pulse. So let's see how the output changes. So we have drawn the clock pulse here. You see, this is an arbitrary pulse, clock pulse, but of course it's a square. With this arrow, we indicate that the output will change only during this time, this change. Okay. So initially, we considered that circuit, again, output of this circuit is as Q1, Q0. Q1 is the MSB. You see here. Q1 is the MSB and Q0 is the LSB. Okay. So now, initially we considered the circuits is in reset condition, that is 0, 0. So we have started here as 0. You see here again 0. Okay. So it will go on as 0. The output of this one. We have kept T0 is equal to 1 and clock changes like this. So initially Q0 is in reset condition. So it will go on like this. As soon as reaches to the negative SD of the clock pulse, you see it was 0, it will go on high state because this is in T flip-flop. This is a T flip-flop, so it will toggle. When this toggling will occur at the negative edge. So again it will go like this. When it reaches another negative edge of the clock pulse, you see from 1 to again it toggles to 0, come back to 0. Then again it will go like this. At this negative edge, again it becomes 1. Again it will go like this. So like this, it will change like this. Okay. Now this is our clock pulse for this one, this circuit. You see, this is our clock pulse. We have connected like this. So again we have given arrow here just to say that this is negative state. So it was 0. So it continues is 0 state until this negative edge of this Q0. So here you see this is 0 till this edge, then again 0. Okay, it will go on up to this edge like this. Now we see what is the states Q1 and Q0 looks like. So say Q1, Q0. Initially you see 0, 0. So 0, 0. Then after one clock pulse, we have this is say 1. Okay. So this is 2, this is 3, this is 4 clock pulse. Okay. So you see after one clock pulse here, if you check the output, you see 0, 1. So this is your 0, 1. After 2 pulse here, if you check, you see 1, 0. So this is your 1, 0. And after 3 clock pulse, 3 means 4 because this is 0, 0 clock pulse. Okay, so after 3 clock pulse, you see 1, 1. So 1, 1. Then after 4th, you see again 0, 0. Again 0, 0. Then 0, 1 like this it will. So this circuit will go on changing its outputs like 0, 0, 0 1 1 0 1 1, then again 0 0. So it has 4 distinct independent states, and the order order of change of the outputs is 0 1 2 3 like this. So this is a up counter 2-bit with 4 states. Okay. So in these circuits, then the pulse you want to count should be given here in the clock input. Okay, so the pulse you want to count, you have to use as the clock, this one of the circuit. Then just observing the output, you can say that how many clock pulse was passed at this point. Okay, so it's some kind of counter, and this is up counter. So then say this is down counter. This is again a 2-bit down counter. 2-bit means 2 flip-flop. So it can count up to 4 states. And since it is a down counter, so counting will be like this: 3, then 2, then 1, then 0, then again 3, 2, 1 like this. So it's a down. So again we use 2 T flip-flop. Same thing is here. Only thing is that here for the second T flip-flop, here we have used Q0 bar as clock. Earlier case we used Q0. Okay, so let's see again. Here output will be Q1, Q0. So let's see how output look like, or how the states change. So this is your clock pulse. Again, this is your clock pulse. So it is a negative SD card flip-flop as shown here. Okay. Now, initially we assume that the states are 0 0. Okay. So you see Q0 is 0 till negative edge of the first clock pulse. So here you see it becomes 1. Arekta clock pulse porjonto, then again 1 till this edge, again 0. Like this it will change. Okay. Now our clock is the bar of this Q0. So we have drawn the Q0 bar. Just এটা উল্টা. এখানে 0 ছিল, you see this is high. This is high, so here this is 0. Here 0, here 1, just opposite. 1, 0, 0, 1, 1, 0 like this. We have drawn. Then we have given this arrow to show that this is a negative triggered signal clock pulse. Now you see initially Q1 was 0 here. So after 1 clock pulse, that is this one, at the negative edge you see 0 to 1 till this negative edge, then 0, then again till this negative edge 1. So it will change like this. Now if you want to read the output or check the states of this counter circuit, you have to check the Q0 and Q1. Okay, so this was our initial state. Okay, so it's directly changes to, you see, 1 1. Okay, so 0 0, then 1 1. Okay, then you see here this is 1 0, this is 0, this is 1. Okay, so your 1 0, then here you see this is 0, this is 1, so 0 1, then here you see this is 0, this is 0, so this is 0 0. After that here you see 1 1, so 1 1. So it's continuously changes its states from 1 1 to 1 0 to 0 1 to 0 0, then again 1 1. That means like this order. So this is a down counter with 4 distinct independent states. Okay. So we said that this is a counter with 4 counts. Okay, and this counts is also known as modulus of the counter. Number of independent states of the counter is also known as modulus of a counter. Okay, so this is a down counter with 4 independent states designed using Jacker flip-flop. So this is clear, Shubhajyoti? Shubhajyoti? Sudeep?
Hello, sir.
Up to this, okay?
Yes, sir. ठीक है, sir.
Okay. So Shubhajyoti may be left. Or sometimes I know कि someone in market or cycling or just keeping mobile switch on go outside or for other works. We also do sometimes for conference, seminar, etc. তোমরাও তো এরকম করো নাকি দা সাগরিকা?
না স্যার।
Anyway, no problem. We cannot do anything. Okay. Still, thanks to the internet, that at least system is moving on. Otherwise, everything should have to in a locked condition. Anyway, so we have seen 2-bit up counter using T flip-flop, 2-bit down counter using T flip-flop. Both are negative SD card. Now we want to see the same thing, up counter as well as down counter using positive SD card flip-flop. Okay, positive SD card flip-flop. So you see this circuit is almost identical with this one. You see, only thing is that here clock pulse is positive SD card. Okay, so here you see, you don't consider this one. Don't consider this one. It will change here only. Here. Okay. Here. So now you see, initially again we considered both the Q1 and Q0 as 0, initially in reset conditions. Okay, so this is a positive SD card flip-flop. So you see 0, it will change here at the positive edge till this positive edge, then again 0, again like this, you see here, then again here. Now here also very similar to this one, clock pulse is Q0 bar, so we have to draw Q0 bar here. You see just ulta 0, ekhane 1, here it is 1, so 0, like this. Okay, so here output will change here, positive edge. So this is your clock pulse for this flip-flop, So initially it was 0, so it will continue its state till this positive edge of the clock pulse. So here it becomes 1, then again it will continue till this edge. Here it will change to 0, so it like this. So now check what is the output, that is Q1, Q0. So initially it was 0, 0, Q1, Q0, 0, 0, this value or this value, 0, 0. Okay, so after one clock pulse, you see here 0, 1. So this is 0, 1. Then again here you see 1, 0, 1, 0. Then here you see 1, 1, 1, 1. Then here you see 0, 0, 0, 0. So it continue changing its states from 0 to 0, 1, 2, 3, then again 0. So this is a up counter, okay, but using positive S triggered flip-flop, T flip-flop. Similarly, you see in this circuit, here is very similar to this one. Only thing, this part is changed. Earlier it was negative S triggered, now it is positive S triggered. You see. So again, if you check the timing circuit, so initially your clock pulse, you see, like this. Then your output was 0, 0. That means Q0, 0. So it will continue up to this positive edge. Then 1. Then up in this edge becomes 0. Then like this. Then here 1. Go on like this. Then here. So it like this. Then based on this, for second T flip-flop, this Q0 acts as the clock pulse here. So based on this Q0 will change. So initially it was 0 till this edge, you see, until this edge, 1. Then 0, continue up to here, it becomes again 0 to 1, because this is positive edge, so it's like this. So now if you again check the, initially it was 0, 0 for Q1, Q0. Then after first clock pulse, you see this is 1, this is 1. So 1, 1. Then second pulse, you see 1, 0. So 1, 0. Then after this pulse, you see 0, 1. 0, 1. Then here you see 0, 0. 0, 0. Here again 1, 1. So it will continue like this, say 1, 1, 1, 0, 0, 1, 0, 0, then again 1, 1. So 3, 2, 1, 0, 3, 2, 1, 0, like this. So 4 unique independent states, but change is from, or counting is from higher to lower. So that's why it is a down counter using positive S triggered flip-flop. So we have seen both positive edge, both up counter as well down counter by using positive S triggered as well as negative S triggered flip flop. So if you want to increase the states of the flip flop, you can just simply add T flip flop here. So you check homework, design a up or down counter having modulus equal to 8, that is counts equal to 8. Okay, you can do it. Okay. So you just analyze this one. This is available in the this Anand Kumar book also. So I have taken all this thing from this book only. Okay. So this is a modified version. Modified version of up down counter using negative SD card flip-flop. So that means for extra circuit diye, using this extra circuit, what we have done here, clock either this Q1 will act as a clock. If Q1 is clock, so this is a up counter. If Q1 bar is the clock, then this is down counter. We perform first two circuits. So just putting M is equal to 1. If M is equal to 1, you see here, this is 1. Okay. And here, this is 1, 0 like this. So this will change as just this one, T. Okay. But if M is equal to 0, then this is always 0. And change will occur like this, Q1 bar. Because then this is 1, here 0, that means 0. Here 1, that means 1. And here it is OR gate, so this will accept either this one or this one. So this is an additional circuit that in same circuit, it's possible to design both up and down counter using negative estigative flip-flop. Now homework, design a bidirectional counter, that is up or down counter using positive staggered flip-flop. This is using negative staggered flip-flop, using positive staggered flip-flop. Design a bidirectional counter using positive staggered flip-flop. This is homework. Okay. So now okay. So you see, যেটা আগে হোমওয়ার্ক দিয়েছিলাম তোমাকে, যে ওই mod 8 counter, you see, you analyze this circuit, draw the timing diagram. Draw the timing diagram. ওই ফার্স্ট হোমওয়ার্ক যেটা দিয়েছি, draw the timing diagram. That means output Q3, Q2, Q1 with clock. Yeah. With clock. Okay, clock bar here. Because this is negative or not clock bar. This is negative sticker flip-flop. That means output will change here only. Output will change here, negative sticker. Okay. So at the same time, you design mod 8 asynchronous counter using positive sticker flip-flop. That means there will be 4 circuits. One is up and down for positive sticker, then up and down for negative sticker. So there will be 4 circuits. So you design all these circuits, then analyze. Okay. So this is one part. Then this circuit. This circuit is a 3-bit ripple counter using D flip-flop. Okay. So in D flip-flop, your output, whatever is here, say 1 or 0, it will go to here after 1 clock pulse. So this is D flip-flop. Okay. So this is again 3-bit synchronous counter using D flip-flop. 2-bit, so you use 2. So you draw the timing diagram for this also. Mod 6 counter. Okay. Design a mod 6 counter. So this is important because for mod 4 you need 2 to the power 2 is equal to 4, 2 flip flop. But for 8 again 2 to the power 3 is equal to 3 flip flop. But for 6 you see you have to use 3 flip flop, but you are not using all 8 states because we know that for 3 flip flops we have 8 states. So how we will change the output as soon as it is 6? Let's see. Okay. So you see here an additional, you see NAND gate is used to clear. We know that using clear or preset, we can make the forcefully the circuit output of any flip flop. Okay, either clear means reset or preset means we can make it set. Okay, in a desired way. Okay. So let's see how it changes. So initially, you see, initially after say all are in reset. Okay. So after one clock pulse, output will be like this 0, 0, 1. Because this is up counter, so counting should be 0, 1, 2, 3, 4, 5. Then about 0. 0 to 5 means 6 independent states. Okay. So after one clock pulse, 0, 0, 1. If it is 0, 0, 1. Okay. That means R is equal to 0. 0, 0, 1. So 0, 1 NAND gate. So this is 1. Okay, R. Then after 2 clock pulse, you see 0, 1, 0. Then again 0, 1, 0. So again here this is 0. Okay, no problem. R or R bar. You can give R bar, that means opposite of this one because we are actually taking R bar. So you can give R bar also. Okay, if R bar, then this is 1, this is 1, this is 1 like this. It will be 0 here. Ulta হইব আর কি, বুঝতে সুবিধা হবে। 3, 0, 1, 1. 0, 1, 1. 1, 1 means here again 0. Then 4, then 5. You see, in case of 5, 1, 0, 1. 1 after 5, 1, 0, 1. Okay. Oh, this is also okay, no problem, because 0, 1, 0 means AND gate 0, so this is 1. Okay. But as soon as till this point, okay, no problem. It is not affecting here. It is not clearing here. As soon as you see become 6, 1, 1, 0. 1, 1. ও না না, এটা উল্টা বোঝাচ্ছি আমি। এটা তো Q3, Q2, Q1. 1, 1, 0. That means as soon as your Q2 and Q3 is 1, then only this R will change. Okay. This R will change as soon as this Q2 and Q3 is 1. Okay. So this will clear here. That is, automatically it will make all the Q1, Q2, Q3 as 0. That means you have to choose these two inputs in such a way that যে অন্য কোনো কম্বিনেশনে যাতে এটা না হয়। অন্য কোনো কম্বিনেশনে যদি if you get 1 1 অন্য কোনো কম্বিনেশনে, then what will happen? Automatically it will clear. So এই যে এখান থেকে খুব টেকফুলি যে কোন দুইটা দিয়ে আমরা এটা করব বা নাকি তিনটা দিয়ে করব সেটা আমরা জেনে নিতে হবে কোন জায়গাতে we want to clear. That is, we want this R bar should be effective. Okay. So here you see this 1 1 only 6. Before that, no 1 1. So it will become 0 0. Then again, automatically like earlier case 0 1 1, 0 1 0, 0 1 1, like again it will move. So this is a mod 6 counter using T flip flop. সাগরিকা, বুঝতে পারছো না এটা?
হ্যাঁ স্যার।
So you can try with or you take it as a homework. Design and implement mod 10. Mod 10 means you need how many flip-flops? You need 3 flip-flop is not enough because 3 flip-flop you have 8 states. So mod 10 means more than 8. Our 4 দিয়ে you can have 2 to the power 4 minus 16 states. So in between you have to modify the circuit. So you need 1, 2, 3, 4 flip-flops. Okay. And in that case, your states will be 0 to 9. 0 to 9, mod 10. 0 0 1. Terminal in such a way that as soon as it reaches this state, it should clear all the flip-flops. That means it should reset all the flip-flops. You have to do some kind of modification here. So you do it. Homework. এটা বইয়ের মধ্যেও করা আছে, ওই আনন্দ কুমার বইয়ের মধ্যেও। Also, you draw the timing diagram for this one, then this one, timing diagram. Then shift register counter. So a counter always need not to change its states like 0 1 2 3 or 3 2 1 like this. I told you at the very beginning that key output should have a distinct independent states, so that just observing the output you can say that yes, this is 1 count, this is 2 count, like this. Okay. So ring counter and twisted ring counter or Johnson counter, these are again another type of counter where the output has some distinct specific sequence, change in a sequence. Okay, but it's not like 1 2 3 4 5 like this. Okay, but of course these have their own advantage as well as disadvantage. We will see it later. So this is a ring counter circuit. You see, this is a D flip-flop. D1, D2, D3, D4. So 4D. So in earlier case, ripple counter or asynchronous counter using T flip-flop or D flip-flop, we have seen that যদি আমরা 4টা D use করি, in that case we could have get we could have got 2 to the power 4, that means 16 states. But here, the output will change in a sequence within these 4 states: 1 0 0 0 0 1 0 0 0 0 1 0, then 0 0 1. Okay, so let's see how. Say, you see, let us consider by some means we have given Q1 is equal to 1. That means using your clear or preset input. Okay. So say Q1 is equal to 1. So before applying any clock pulse, state of this circuit is Q1, Q2, Q3, Q4 as 1, 0, 0, 0 like this. So once you apply first clock pulse, you see here Q4 0, that means it is 0 here. Here 1, that means 1 here. So after first clock pulse, this 0 will be transferred here and this 1 will be transferred here. You see 0, 1, 0, 0. Then again 0, 0, 1, 0. Then again 0, 0, 0, 1. It will go, this 1 will go on shifting or circulating. Okay. Then again you see 0, 0, 0, 1. Then when it's like this 0, 0, 0, 1. That means 1 here. So after again clock pulse, this 1 will come here. Then these are 0. You see here. So it will continue moving within these 4 states. So in that case, for a ring counter, you need the number of flip-flops to have a particular count to the number of counts. Count or number of flip-flops is same. So this is uneconomical if you consider with respect to ripple count. But the good thing is that in case of ripple counter, what you need decoder, because these are binary or digital systems and the output is in coded format. But here, just by observing which flip-flop is set, you can have idea about the state. So you don't need the decoder. This is the advantage. Okay. So you can design the same circuit using JK flip-flop also. In that case, what you have done, you see, you have done some feedback like this and here like this. Then clock. Then in JK 1 0 output is 1 0. 0 1 output is 0 1. So like this. So if you analyze, you will have a function table very similar to this one. Okay. So this is the timing diagram. After, you see, initially it was 1. Again after 1, 2, 3, another 3 clock pulse, you see this is 1. And then here you see after 1 clock pulse, this one is shifted 1, you see here. Then again this will, after 3 clock pulse, it's like this. So this is the timing diagram of that one. So this is your ring counter. Okay. Then twisted ring counter. Okay. So this is some modification of the earlier circuit. Earlier case, we have seen that the input was connected with Q4, but here Q4 bar. Q4 bar. Okay. So it's connected Q4 bar. Okay. So in that case, you will see that here your circuit has 8 independent states. Earlier it was having 4 independent states, but here it have 8. So this is more economical with respect to your this ring counter. Johnson counter is more economical because ring counter you have 4 counts. For having 4 counts, you need 4 flip-flop. 5 counts, 5 flip-flop. But here you see count is 2 to the power n. Sorry, twice n. Here count is, in case of Ripple counter, 2 to the power n, where number of flip-flop. In case of rim counter, only n. In case of Johnson counter, this is twice n. Hang kora jayega ki? In case of this counter, this is twice n. So this is good with respect to this one. So here you see, after say initially all the states are in reset conditions. So before applying any clock pulse, that is 0, you see 0, 0, 0. Then after first clock pulse, if all are 0, that means here 1. So this 1 will go here. So after first clock pulse, this 1 will go here. So you will have a output like 1, 0, 0, 0. Then after second clock pulse, again, here it is 1. So this one will go here, but this one will go here. So this is 1, 1, 0, 0. So in this way, 1, 1, 1, 0, all 4 will be set. Then again, it will go towards reset. Okay. So it will move or continue changing its states from 0, 0, 0 to 1, 1, 1, 1, then again 1, 1, 2, 0, 0. So it has 8 states. Okay. So if you use n number of flip-flops, you will see that your circuit has twice n number of counts. So this is more or less better with respect to your Ripple counter. Okay. So this is the timing diagram, and this is the twisted ring counter using JK flip-flop. This is using D flip-flop. This is again JK flip-flop. So you analyze this circuit, then draw the timing diagram of this circuit. Okay. Okay. So okay, so let us stop here today. Okay, tomorrow we will continue our discussion on this decoding, that is decoder or and encoder, as well as shift register. So we will continue discussion in this topic next class, Monday. Okay, and next Monday we will take a small exam, maybe 20 minutes. Okay. Sudeep, do you have any suggestions?
স্যার
হ্যাঁ কো
গুগল ফর্মে হবে এক্সাম নাকি আমাদের মানে কোশ্চেন দেওয়া হবে আমরা পিডিএফ করে দেব?
না গুগল ফর্মেই হোক আর গুগল ফর্মেই চেষ্টা করব, যেটাই হোক, হোয়াট এভার মে বি, ইট উইল বি অন ভেরি শর্ট। ওকে, বাট অ্যানাদার ইস্যু ইজ কি এই টপিকের মধ্যে তো তোমার বেশিরভাগই সার্কিট টার্কিট এগুলো আঁকার ব্যাপার আছে, ঠিক আছে? চিন্তা করে আমি 2 দিন আগে জানিয়ে দেবো তোমাদের, আমি নেক্সট ফ্রাইডের মধ্যে জানিয়ে দেবো। বাট যেটাই হোক একটু সংক্ষেপেই হবে আর কি, ঠিক আছে?
ওকে স্যার।
যতটুকু আজকে অবধি পড়িয়েছি, পরীক্ষার পরে আমরা ওইটা কমপ্লিট করবো, ওইটা ঠিক আছে। আর আরেকটা ব্যাপার, ওই সিলেবাস কিন্তু অগাস্টের মধ্যেই কমপ্লিট করতে হবে যতটুকু হয় আর কি, চেষ্টা করতে হবে অগাস্ট। কারণ শুনলাম একটা নোটিফিকেশন এসছে যে অগাস্টের মধ্যেই কমপ্লিট করতে হবে, বুঝতে পারছো ওটা? কাজেই নাকি অগাস্টের মধ্যে পরীক্ষা, আমি জানি না। আগে শুনছিলাম সেপ্টেম্বরে হবে, এখন শুনছি যেমন অগাস্টে হবে। কাজেই তোমরা